Hello, Calculus BC. I'm here with you today for a lesson. So as you guys saw in the homework last night, there was one problem that had to do with logistic differential equations. And you might be curious, what is a logistic differential equation? Well, I waited for this until the end of the year because it does really relate to anything else we do this year. Logistic DEs are not really something you're going to solve algebraically. It's more just like a series of observations and patterns that you want to understand. So a logistic DE falls in a specific form, but the important thing is what it represents. So if you have a logistic differential equation, logistic DE, a logistic DE represents some sort of population. So a population of something. Maybe it's animals, maybe it's people, maybe it's a virus, who knows. The form that these are going to be written in is always going to look the same, although there are some variations. So in my form, we're going to say A and B are going to be positive constants. So this is a differential equation. You might see it written like dy dt equals ay minus by squared. So one thing worth noticing in this equation, there's no t. There's no time variable. The rate of change is wholly dependent on what the current population is. Some other examples you might see, you'll oftentimes see a factored form. So dy dt is say like ay minus ay times b minus y. And then another form you might see is say dy dt is equal to a times y times 1 minus y over b. But notice on all these, if you factor them out, they're all kind of going to come back to this same form right here. So you might see, again, some forms with actual numbers, some that might be factored. So dy dt is equal to 3y minus 400y squared. A lot of times we'll put a p for a population, like dp dt is, say, 1/3 p times 100 minus p. Okay, so those are examples of logistic DE because they all follow that form when you go out. So it's basically saying, the rate of change is based on the population and then some amount of population that we don't have yet. So let me get an example here. Here's a slope field for this. So the DE is 2p times 4 minus p. I want to go ahead and draw some solution curves here. We only really care about the first quadrant. This is like a t and this is like a p on the y-axis. And the reason we only care about the first quadrant, right, is we're not caring about negative time and we're not too concerned about negative population. If we're talking about rabbits, it doesn't make any sense to have negative rabbits. Okay, so in terms of what is happening, notice this. If you were to start on this line 4, it actually is a horizontal solution curve all across. So that's me starting at 0, 4. But look what happens if we start at other points. So I also asked you to start at 0, 1, 0, 2, 0, 3, and 0, 5. Okay, so if you start at 0, 1, we see the solution curve is kind of going to have this shape going down to the left. But then as we go to the right, it goes up quickly like that. And then it kind of flattens out a little bit, something like that. If you start at 2, you go up, and again, it kind of reaches the same shape. You get to this asymptote at the value of 4. And what I'm hoping you'll notice is that all these solution curves actually have the same shape. They have the same shape in any solution to logistic DE. If we start say at 4, 2, we're going to recognize the exact same thing. It goes up and then starts to flatten out, and then it goes down, and then it just kind of flattens out as we go over to the left. They all have the exact same shape here. So in terms of this, what is the limit as t goes to infinity? What you should recognize, I forgot to see the one up here at 5. 5, we see it just goes down and then reaches that asymptote there. The idea is the limit as t goes to infinity of p of t, p being a solution. So the p is the solution in this slope curve for dp dt. That limit is going to 4. All those are going to a height of 4. For what values of dp or p is dp dt equal to 0? So looking at this equation, you say where does 2p times 4 minus p equal 0? So that's saying your p is equal to 0 or your p equals 4. So notice it's one of the same points. What happens to p prime of t as t goes to 0? Well, you guys should notice these all flatten out, right? So this is talking about the slope. So the slope, if you take that limit as t goes to infinity of any solution curves, that slope is going to 0. So as we approach a p-value of 4 or so something like that, we see the slope's going to 0. Okay, so let's go ahead and really, again, our goal is to kind of learn about the shape of these curves, the properties of these slope fields and solution curves for logistic DEs. We're not necessarily going to be solving problems. So let's talk about some observations and patterns. So what we saw as we work through this, and if this were in class, I would have had you kind of like draw these solution curves and fill it out yourself, is that as t goes to infinity, all the graphs of p of t approached 4. Approached a height of p is equal to 4. Now this p equals 4 is what's called in your environmental science class a carrying capacity. Okay. And what a carrying capacity represents is it's kind of like the max population, the maximum population based on the available resources. So in terms of a real life thing, it's like how many wolves can this area support just based on how much food there is, how much space, how much shelter, that kind of thing. How many rhinos can this support? That's the carrying capacity. Okay, to find this carrying capacity, all you do is you set the dp dt equal to 0. One of the solutions is going to be 0, and the other one is not. So that's kind of saying on this graph, this is my carrying capacity. When you got the derivative as 0, that happened to p equals 0 and p equals 4, that's your carrying capacity. So what that's saying is, if you're below it, you kind of go up to that carrying capacity. If you're above it, you go down to it. So basically what you can think of here is like, if you're above the carrying capacity, there's not enough food, so your animals are going to die off. That population decreases as you get close to it. If you're below the carrying capacity, there's plenty of food, there's plenty of room, so these animals are going to continue to reproduce and make more as we go on and approach that carrying capacity. And then it's kind of like a steady state. Once you're at that 4, you just kind of chill at that 4. Obviously, it's not exactly what's going to happen, but it's a pretty good mathematical model. Okay, so let's go on and talk about a couple other things. So as t goes to infinity, so as you go on infinitely long in these models, your p of t is going to go to your carrying capacity, or your CC if you want. And your p prime of t is going to go to 0. And like we were saying, basically the population stops changing. The birth rate and the death rate are going to be roughly equivalent at that point. Now, another important thing, is as p grows, it grows the fastest, meaning it has the steepest slope at the carrying capacity divided by 2. So thinking about these solution curves, they all have that same shape, right? So if you have this graph, like let's say you have a carrying capacity up here. Okay, so when you have this curve, the general solution curve for all these looks like this. And the point where it goes fastest, where you have the steepest slope, is the inflection point right there. And that happens at the carrying capacity divided by 2. Okay, and you can actually show that if you want by taking a second derivative and seeing where that's equal to 0. But sure enough, you'll have your inflection point always at half the carrying capacity. Okay, so in terms of the shape of the graph is concave up on the interval from 0 to the population to the carrying capacity divided by 2. It's concave down on the interval from the carrying capacity divided by 2 to the population to the carrying capacity. And we see that on our graph, right? Where is it concave up versus where is it concave down? Okay, one other thing worth pointing out, with this model, you have a rate of change of 0. It's like if you start with 0 water buffalo in Santa Clarita, you will continue with 0 water buffalo. They're not going to kind of appear out of thin air. Okay, so that's kind of what's going on here. Let's go ahead and talk about an example problem. So I doubt you'd see a full FRQ on this, but it's very possible you might see part of an FRQ. So let's look at what that might look like. So suppose I tell you dy dt is equal to 2y times 2 minus y over 400. And let's say this models, the population of hippos in Valencia. As you guys know, a lot of hippos in Valencia these days. We need to model them and come up with some math so we can figure this out. And I'm going to say y equals f of t is the particular solution with f of 0 is equal to 100. So that's just saying we have a starting population of 100 hippos in Santa Clarita, which is probably a little on the high end, but you know, it is what it is. Okay, so part A, we're going to ask ourselves, is this logistic? So does it follow that form? And when you're checking if something's logistic, you want to multiply it out. It's going to be like, again, ay minus by squared. So if you distribute this out, you get dy dt equals 4y minus 2y squared over 400. Check. It's in the right form. Great. Okay. Now part B of my hypothetical problem tells you this. Think of the kind of shape of the graph as you find the limit as t goes to infinity of this f of t, this particular solution, and the limit as t goes to infinity of f prime of t. And again, the way you want to do these problems, you're not like really doing a bunch of math here. I want you to think about the slope fields and the solution curves. Slope field and solution curve. Okay, so what it's going to look like, and this is true for every single logistic DE. They all have the exact same shape of the solution curve, right? You have some carrying capacity. And then what you have is you have this concave up part, and then it reaches the inflection point half the carrying capacity, and then it starts to flatten out. Okay, so if you take that limit as t goes to infinity, no matter where you start of f of t, that's going to equal the carrying capacity. Okay, so let's find the carrying capacity. The carrying capacity is when the population stops changing. So that's when your dp or your dy dt equals 0. So looking up in my equation, that's when 2y times 2 minus y over 400 equals 0. Okay, so either 2y is 0, but that's not the carrying capacity. That's just saying if you start with 0, you end with 0. Or 2 minus y over 400 equals 0. You add this, you multiply, you get y is 800. That's the carrying capacity. So that's saying that this limit is 800. Okay, so that's telling you that 800 is like the carrying capacity of this graph. And then the second part, if you take the limit as t goes to infinity of f prime of t, that slope is always going to 0. There's no real work to show. You just kind of need to know the pattern for that. Okay, so let's go on to the next part. The next part of my problem is going to say C, for what value of P, or I guess Y, should use Y, for what value of Y, this population, is the population growing the fastest? Okay, and again, there's no real calculus to show. It happens at half the carrying capacity. So that's 800 over 2, the one you just found, which is 400. Okay, and then the other answer that I wanted to give, or the other question I wanted us to think about is like, if we start with f of 0 equals, I don't know, like 3,000, does that affect part B? So does it affect the long-term limit? And the answer there is no. Because if you, again, think about this, you have your carrying capacity at 800. That's your carrying capacity. If you start above this, if you start way up here, you're still going to go down to that same thing. No. The limit as your t goes to infinity of f is still going to 800. The limit as t goes to infinity of f prime, that slope is still going to 0. And that's true no matter where you start. If you start really close to carrying capacity, it just goes up to it like that and follows it. If you start down here, it goes that same kind of like inflection point thing, and then it kind of flattens out. So that's the key, is knowing the shape and some of the patterns. This idea that the solution curves are going to follow like this shape no matter what. As they approach that carrying capacity, which is where the dp dt is 0. So that should be able to help you out in a lot of these problems. I hope you enjoy logistic DEs. Good luck on the homework, and stop by office hours or whatever if you got any questions. Talk to you soon.